All right, so you really want to understand principal component analysis.
PCA.
Yeah, PCA as it's known, in the data world.
Right.
And it's basically a way to simplify these really complex data sets.
Yeah.
And you sent over some really great notes and images that we're going to use to kind of take a deep dive into PCA today.
Yeah, I'm excited.
Yeah, and basically imagine if you had a house and it was described by 500 different features.
Wow.
From like the number of bedrooms to like the size of the backyard fountain. And PCA can help us condense all that information down to maybe just a handful of key factors without sacrificing too much accuracy. Pretty cool, huh?
Yeah, it's really fascinating. Actually, PCA has revolutionized fields like genetics where researchers can use it to identify population groups or even trace ancestry by highlighting these subtle patterns in genetic data.
Oh, wow. Okay, so that's already blowing my mind.
Yeah.
But before we jump into like how PCA works,
Right.
I'm curious about why we even need to simplify data in the first place.
Yeah.
Isn't more data always better?
That's a good question. And that's not necessarily true. You might run into what's called the curse of dimensionality.
Whoa.
It sounds pretty dramatic.
Yeah.
But it basically means that having too many features can actually make your analysis less effective.
Okay.
So imagine trying to find a specific book in a library with millions of books, but no organization system.
That just sounds like a nightmare. You'd spend years searching and probably never find the right book.
Exactly.
Yeah.
And that's what can happen with machine learning models. When they have too many features to process the models, get bogged down by all the noise and all the complexity, and their performance actually starts to suffer.
So it's like trying to make sense of a symphony orchestra when like every instrument is playing at the same time.
Mm-hmm.
You need some way to separate the melodies from the noise.
That's a great analogy. And that's where dimensionality reduction techniques like PCA come in.
Okay.
They help us filter out the noise and focus on the most important signals in the data.
So how does PCA actually do that?
Yeah.
Does it just randomly discard features?
No, it's much more strategic than that. PCA focuses on finding the most informative directions in the data, the ones that capture the most variation.
Okay.
Think of it like finding the main streets in a bustling city.
Okay.
Those streets with the most traffic and activity, those are your principal components.
Okay, so it's not just about reducing the number of features, but about finding the features that really matter, the ones that explain the most about our data.
Precisely. And those principal components are represented by something called eigenvectors.
Eigenvectors.
Yeah, they tell us the direction of those main streets.
Okay.
And each eigenvector has a corresponding eigenvalue, which tells us how much traffic flows along that street.
So eigenvalues help us like rank the importance of each principal component.
Exactly.
It's like knowing which ingredients contribute the most to the flavor of a dish.
Yeah.
You wouldn't want to leave out the main ingredient, but maybe you could skip a pinch of salt or something.
Exactly. And by focusing on the principal components with the highest eigenvalues, we can reduce the dimensionality of our data while preserving the most important information.
Okay, now I'm really curious about how PCA actually figures out these eigenvectors and eigenvalues. I'm guessing there's some math involved.
There is, but the core concept is actually quite visual. Remember when we talked about the data being spread out like a cloud of points?
Yeah, like a big cloud.
Well, the covariance matrix captures how tightly those points are clustered along different directions.
Okay, I'm starting to see where this is going. So by analyzing the covariance matrix, PCA, can identify the directions with the most spread, which become our principal component.
You got it. And those directions are represented by the eigenvectors.
Yeah.
And the amount of spread in each direction is represented by the eigenvalues. It's all connected.
It's all connected. So we're essentially finding the axes of this data cloud, where things are most stretched out, and those become our principal components.
That's a great way to think about it, yeah.
And then by projecting all of our data onto these new axes, we're reducing the number of dimensions, but keeping the most important information.
Precisely. It's a bit like taking a 3D model of a city and flattening it into a 2D map,
Okay.
but making sure to preserve the locations of the most important landmarks and streets.
This is all making a lot more sense now, but I'm curious about how we decide how many principal components to actually keep.
Right.
We could reduce everything down to just one dimension,
Yeah.
but wouldn't we lose a lot of information that way?
That's a great question. It's a bit of a balancing act. We want to simplify our data enough to make it manageable, but we don't want to oversimplify and throw away valuable insights. One way to approach this is to look at the explained variance ratio.
Explain variance ratio. What's that?
It tells us how much of the total variation in the data is explained by each principal component.
Oh, okay.
So, for example, the first principal component might explain 50% of the variation, the second might explain 25%, and so on.
Okay.
We can then choose to keep enough components to explain a certain percentage of the total variance, like 90% or 95%.
So we're aiming for like a sweet spot where we're capturing most of the important information while still reducing the complexity of the data.
Exactly. It's a bit of an art and a science,
Yeah.
and the ideal number of components will depend on the specific data set and the goals of the analysis.
Now, I've heard PCA mentioned in a lot of different contexts, from facial recognition to stock market analysis. Can you give me some concrete examples of how PCA is actually used in the real world?
Absolutely. One really interesting application is in image compression.
Okay.
PCA can be used to represent images with fewer bits of information, which is essential for storing and transmitting large image files efficiently. Think about how much data your phone uses when you're streaming videos or scrolling through social media. PCA is working behind the scenes to make that all possible.
Wow. I never realized PCA was involved in something as everyday as watching videos on my phone.
It's everywhere. Another really cool application is in recommender systems. Those algorithms that suggest products you might like or movies you might enjoy.
Yeah.
PCA can help identify underlying patterns in user preferences and create more personalized recommendations.
Well, PCA is basically the engine behind my Netflix recommendations. That's kind of creepy, but also really impressive.
It is pretty fascinating how these algorithms can learn our tastes and predict what we'll enjoy.
Yeah.
And PCA plays a key role in making that happen.
Okay, so we've covered the basics of how PCA works and some of its real-world applications, but I'm also wondering about its limitations.
Yeah.
Are there situations where PCA isn't a good fit, or are there potential pitfalls we need to be aware of?
That's a great question. And it's important to remember that PCA isn't a magic bullet. It's a powerful tool, but it has its limitations.
Yeah.
One thing you keep in mind is that PCA assumes that the relationships between features are linear. So if the underlying patterns in your data are highly nonlinear, PCA might not be the best choice.
So it's like trying to fit a square peg into a round hole.
Exactly.
PCA works best when the data conforms to its assumptions.
Yeah. Exactly. Another potential pitfall is that PCA can be sensitive to outliers. Those data points that are significantly different from the rest, if your data set has a lot of outliers, they can distort the principal components and lead to misleading results.
So it's important to clean and pre-process our data carefully before applying PCA, just like with any other machine learning technique.
Absolutely. Data preparation is always crucial for ensuring accurate and reliable results.
This has been a really enlightening deep dive into PCA. So far, we've gone from the curse of dimensionality to the geometric intuition of eigenvectors and eigenvalues, and we've even explored some of its real-world applications.
And we've only just scratched the surface. There's so much more to discover about PCA and its connections to other areas of data science and machine learning.
Before we wrap up, I have one final question that's been on my mind. So we've talked about how PCA can simplify these complex data sets
Right.
and even help us understand things like facial recognition and recommender systems, but could it also be used to analyze and understand something as complex as like human behavior?
That's a really interesting question, and it's definitely something that researchers are actively exploring.
Okay.
Like imagine using PCA to analyze data from wearable sensors, social media interactions, purchasing habits, all those digital breadcrumbs we leave behind every day.
Yeah.
Could we potentially identify underlying patterns and gain insights into how people behave?
It sounds like something out of a science fiction movie,
Yeah.
but also kind of exciting.
It is exciting.
Like, could PCA predict things like what book I'll want to read next or
Well-
where I'll go on vacation or...
It's certainly a possibility,
Okay.
but we have to be careful about oversimplification.
Yeah.
You know, human behavior is influenced by such a complex web of factors:
Yeah.
genetics, upbringing, social influences, personal experiences, even our current mood.
Right.
Reducing all that complexity down to just a handful of principal components could lead to some misleading conclusions.
Right, like those personality quizzes that claim to know everything about you based on your favorite ice cream flavor. Fun, but probably not super accurate.
Yeah. Exactly. PCA can reveal some really interesting patterns, but it's important to remember that correlation doesn't equal causation.
Yeah.
Just because we see a relationship between certain variables doesn't mean that one is directly causing the other. There could be hidden factors at play, or the relationship could be purely coincidental.
So while PCA can be a valuable tool for exploring and analyzing human behavior data, We need to be cautious about making predictions about individuals based solely on this simplified representation.
Absolutely. It's crucial to approach such analyses with a healthy dose of skepticism.
Okay.
And to be mindful of the potential impact of these insights, we need to ask ourselves who is benefiting from this knowledge and who might be harmed.
Yeah.
Are we respecting individual privacy and autonomy?
It sounds like PCA is a tool that requires not just technical expertise, but also ethical awareness.
Well said. It's a reminder that data analysis isn't just about crunching numbers. It's about understanding the real-world implications of our work
Yeah.
and using our knowledge responsibly.
This has been an incredible deep dive. We've covered the mechanics of PCA, its wide-ranging applications, and even touched on some of the ethical considerations that come with using such a powerful technique.
We've gone from the curse of dimensionality to the elegance of eigenvectors and eigenvalues, and we've even glimpsed the potential of PCA to unlock the mysteries of human behavior.
That's right. And if there's one thing I hope you take away from this deep dive,
Yeah.
it's that PCA is a fascinating and incredibly versatile tool with the potential to revolutionize how we understand and interact with the world around us.
And like any powerful tool, it's up to us to use it wisely and ethically.
Well said. Well, thanks for joining us on this deep dive into PCA.
My pleasure.
We'll see you next time for another adventure in the world of data.